So, good morning everyone. Today we are going to learn about the preformulation studies. So, what are preformulation studies? Branch of science which deals with the physico-chemical properties of drug substances, new molecular entity. So, what is new molecular entity? So, if you are going to prepare a drug, so this drug is already not existing earlier, and you are preparing for the first time. So, this drug will be the new molecular entity. Okay, so new molecular entity and active pharmaceutical ingredients or medicament is called preformulations. Active pharmaceutical ingredients or medicament is called preformulations. Okay, now the most important point we are going to learn is that what are the physicochemical process. So physicochemical process are mainly of three types. Physicochemical process mainly of three types. Number one, bulk properties. It has three properties. Number one, bulk properties, solubility properties, stability properties. In bulk properties you will see the totally large amount. For example, a substance, before preparing a drug you will have some substance. First of all, you have to arrange the raw materials or crude drug. So in this you can understand in bulk amount. So what you can understand in bulk amount? Number one, crystallinity. For example, you have taken some substances, whether they are crystalline or amorphous, or they have polymorphism. Polymorphism means they have single structure but different characters or different shape. Okay, so polymorphism, normally they are the drug or medicament, active pharmaceutical ingredients, any substance exhibit two structure. So they have more than one structure or the shape and different characteristics, but they have ultimately same. They are same in their characters. So polymorphism. So you can see their crystallinity, ultimately their structure, whether they are amorphous or crystalline. Number two, hygroscopicity. In this hygroscopicity, what does hygroscopicity mean? Hygroscopicity means how much amount of water it can absorb, water particles it can absorb from the environment. Okay, next is you can see that fine particle characterization. Fine particle characterization means you have taken some substances, you can using friction or any types of ball mill, hammer mill, you can particulate them. You have to make them small smooth particles. So when you decrease the size and it will become the fine particle, what will happen? The surface area will definitely increase. When the surface area will increase, it will show its physical character more. Okay, because physical character is directly proportional to surface area. Next, powder flow properties and bulk density. So these all are about bulk properties. Next, you will see that solubility properties. So what are the properties which are related to solubility of that chemical substance or active pharmaceutical ingredients or excipients? Active pharmaceutical ingredients and excipients both are different, but when both of them mix together, they combining both of them, active pharmaceutical ingredients and excipients, one can prepare the drug or any medicine. But active pharmaceutical ingredients is the main substance. It is the it will show the pharmacological action in the body. For both physical bodies have to be related. So active pharmaceutical ingredients will show the pharmacological action in the body, whereas excipient are the other things which doesn't show pharmacological action in the body, but it will have effect on the dosage form. How it will have effect? Maybe it will mask the odor, or maybe it will increase the density, or what it is called, viscosity. It will decrease viscosity, it will increase solubility, and all these things. Okay, these all things are related to excipients are not the active pharmaceutical ingredients which doesn't show any pharmacological action on the body, whereas active pharmaceutical ingredients will show pharmacological action on the body, and both of them will mix together and form the drug or dosage form. Next, stability properties. What are stability? First of all, what is stability? Stability means how much the substance will become stable, how much it will remain stable. For example, you are preparing a drug, it will become stable for 3 years, 5 years, 7 years, 10 years, like this. So stability is how much it will stable. In general, never a drug never stays stable after 2 years, like 3 years, 5 years, 7 years, 10 years, like this. Normal or maximum of the medicine have 24-month warranty, like 24-year their shelf life, or it is called their lifespan. How much? 24 months, sorry, 24 months. So stability means how much the substance will remain stable, whether it will react with any other substances or any other particles present in surroundings. If you keep it in the environment, how much substance it will stay stable, it will react with others, or it will become stable like this is the stability. And stability is mainly defined by three things: hydrolysis, oxidation, and photodegradation. Already I told you that it will react with the substances, or it will react with the its environmental properties or not. So when it will react, for example, corrosion, oxidation, reduction, hydrolysis, dehydration, all these things, even hygroscopicity. In the hygroscopicity, what will happen? It has two parameters, like two types. One is physical. In physical, for example, you take sponge or any dry substance, definitely it will try to absorb water. In it is physical parameter. But chemically also, the water particles will react with the substance. If any organic matter is there, organic particle, maybe it will react with the water particle and make hydrogen bond, and it will become stable. So this addition, like addition or removal or gaining of any substance, is totally related to the stability. All the chemical reaction which is taking place on the environment, on the earth, in the surroundings, okay, in the atmosphere, anywhere, why these all reactions are taking place? Due to the stability only. To gain the stability, any substance, if it is unstable, it will try to react with others, and it will try to make itself stable. So it is all about stability. So stability is a very important property which defines the shelf life or life cycle or expiry of a substance. Okay, so stability is defined by hydrolysis, oxidation, photodegradation. Hydrolysis means addition of hydrogen, removal of oxygen. Oxidation, addition of oxygen, removal of hydrogen. Photodegradation, by sometimes you will see in the chemicals, it is written on the out level that don't put it in the sunlight. So in that case, what will happen? This chemical will photodegrade. In the presence of sunlight or in the presence of light, they will destroy, like they will damage. Why they will damage? Because they are all these things are chemical substances now. That means they are all chemical compounds. So chemical bonds are present in between them. So when the light will fall on that, the chemical bond will break down and ultimately denature the substances. Okay, so that's why photodegradation is very important. Solubility property is most important. It is also very much important property. Why? Because if you are preparing a dosage or solid dosage form, like tablet, capsules, in tablet, what will happen? When you will take the tablet, it will go to the stomach. After going to the stomach, it should dissolve. It should dissolve with the water, or it should dissolve with the fluid which is present in the stomach. After dissolving, it will be absorbed. Yes or no? So for example, I'll show you. For example, so you have taken a drug, tablet. This tablet will go to your stomach. Yes or no? So in the stomach, what will happen? It should be absorbed. So before absorption, it should be soluble to the fluid which is present inside the stomach. After solubilization, after dissolving, it will be absorbed in the circulatory system. And when it will be absorbed in the circulatory system, it will be distributed to the other part of the body. From the circulatory system or through the circulatory system, it will be distributed to other part like liver, or you can say it will be going to kidney also, and also it will be going to other part like skeletal muscle or anywhere. Yes or no? So solubility is very much important. Okay, so solubility properties are studied by, first of all, understanding the solubility, then partition coefficient, then ionization, then dissolution. Obviously ionization will be important for the solubility. Okay, next we are proceeding further. So let's learn the bulk properties. So in these bulk properties, first of all, we will see the polymorphism and crystallinity. So what is polymorphism? Polymorphism, already I mentioned you earlier. Poly means many, morph means structure. So polymorphism means they will have many structures, more than one structures. Okay. So the drug or medicament or active pharmaceutical ingredients, any substance exhibit two structure or more than one structure. One will be external, one will be internal. In external, it is called habit. External structure, it is also called habit. Internal structure is the arrangement of the molecule can be in the internal structure. For example, take a cube. So it will exactly look like cube, yes or no? But when you will see the internal structure, this is the external structure, cube. But when you will break down and you will look into the cube, inside the cube, what will happen? It may be like this. Particles may be arranged like this systemically. So like this, and like this particle may be arranged, or particles may be scattered, or particle may not be arranged systemically. So these things is about internal structure. This is about external structure. This external structure is also called habit. Okay, whereas the internal structure is directly dependent on the arrangement of the particles or molecule. So arrangement of the molecule can be again regular or irregular. Just I have mentioned, see, regular, I just told that systemic, but here it is written regular. So internal arrangement may be regular or irregular. If it is regular, then it is called crystalline. Crystalline morphology, it exhibits polymorphism. Whereas if it is irregular, then it is called amorphous, and amorphous doesn't exhibit polymorphism. So polymorphism is dependent on the arrangement of the molecules inside the structure. Okay, externally it can be cuboidal, it can be needle-like, it can be pencil-like, it can be plate-like, it can be star-shaped. This is the shape, but it is in the internal structure or internal arrangement. There could be different arrangement. One is regular, one is irregular. Regular, crystalline, and which exhibits the polymorphism. Whereas irregular, if it is irregular, then it is called amorphous, and amorphous doesn't exhibit any polymorphism. Okay, the most important point here you have to remember, that is asked in the question, is this one. What's that? The external habit. So needle like, or it is called acicular. Example is nalidixic acid. Example is nalidixic acid. It is tubular, then it is called tolbutamide. So example, tubular shape is tolbutamide. Tubular shape is tolbutamide. Needle shape is nalidixic acid. Okay. And another important point here, the physiochemical properties of drug, which helps to decide the type of dosage form. Okay, which physiochemical properties of drug which decides the type of dosage form or route of administration. Okay, so drug or drug excipient compatibility. Yes or no? Next, it will also define the stability product and then the shelf life predict. Already I have mentioned few minutes ago about shelf life and stability and all these things. Okay, so the route of administration or dosage form or stability predict, all these things are decided by what? All these things are decided by route of administration and type of dosage form are decided by physiochemical properties of the drug. It is decided by physiochemical properties of the drug. The most important, we are going to learn the most important topic, that is clinical trial phases. What are the different clinical trial phases? There are 5 clinical trial phases. In this, the 5 clinical trial phases are phase 0, phase 1, phase 2, phase 3, phase 4. Phase 0, phase 1, phase 2, phase 3, phase 4 are the 5 clinical trial phases. In the phase 0, it is called as microdosing studies. Phase 0 is also called microdosing studies. Phase 1 is called nothing, but phase 2 is called unicentric, phase 3 is called multicentric, and phase 4 is called post-market studies. In this post-market studies, what will be there? There will be different review system, and if the drug has any side effect or anything, then it will be mentioned, it will be noted down, and it will be worked on it. Okay, so phase 4 is post-market studies. Now remember that phase 0 is first step. How many steps are there? There are 5 clinical phases. How many phases? 5 clinical phases. First phase is called phase 0. Phase 0 is also called microdosing studies. These microdosing studies are mainly done on the healthy volunteers. Microdosing studies are mainly done on healthy volunteers. Okay, it is most important to understand that it is already previously asked question that microdosing studies is done on healthy volunteer or patients. So microdosing studies is done on healthy volunteer, whereas unicentric studies is done on patients. Multicentric also patient. Post-market studies also patient. Okay. Now microdosing studies. In microdosing studies, what is happening? In microdosing studies, a 1/100th of actual dose is given and pharmacokinetic data is collected. 1/100th dose of actual dose is given and pharmacokinetic data is collected. Okay. Phase 1 study is also called maximum tolerable dose study. Okay, so maximum tolerable dose of a drug is defined by, or it is determined by, phase 1 study. Okay, am I audible? Next, phase 2 studies. It is also called unicentric studies. Phase 2 is also called unicentric studies. In this, patients are almost 100 to 300. So it is done on the how many patient? Unicentric studies is done on almost 100 to 300 patient. Unicentric studies is done on almost 100 to 300 patient, and it is also called safety preliminary efficacy. Safety preliminary efficacy. Okay. Next, phase 3. Phase 3. Phase 3 is actually fourth phase. So phase 3 is called multicentric. Why it is called multicentric? Acha, listen. Unicentric means it will be done in only one area, in single area, or in single hospital or single healthcare area. Multicentric is done in different areas. For example, in India, a drug is manufactured, or after the compounding of a drug, you need to study on it. You need to do some study on it. So after preparing or compounding the drug, first of all it will be the microdosing studies will be done. After microdosing studies, unicentric studies will be done. This unicentric studies is done in only one healthcare area. For example, in AIMS Delhi, only one, in Delhi only. It will not be done in the other part of the India. After that, phase 3 is done. Phase 3, that is multicentric studies. So phase 3 multicentric studies is done in different areas. After that, what will happen? The dose will be distributed to the other part, other government part. Okay, so it will be given to Telangana, Tamil Nadu, Hyderabad, Karnataka, like this, Guwahati, and then this dose will be used on the different patient. So multicentric studies will be done on how many patient? 1000 to 3000 patient. How many? 1000 to 3000 patient. So why 1000 to 3000 patient? Because some patient will be in Delhi, some patient will be in Tamil Nadu, some patient will be in Telangana, some patient will be in Guwahati, some patient will be in Mumbai, like this. And this step is called safety and confirmatory efficacy. Safety and confirmatory efficacy. After that, what will happen? After safety and confirmatory efficacy, if this drug has no large amount of side effect, or if this drug is not showing any side effect, then this drug will be confirmed that yes, this drug is acting properly. Then this drug will be selected and test data passed. Okay, next is post market studies. After the marketing of the drug, post market studies will be done. Post market, that is phase 4. It is done on the market, that is it will done on the patients, more than 20,000 or 30,000 patients. That means the doctors are prescribing this drug continuously to the patient, and patients are not getting affected by this drug, like they will also get the positive effects. But if this drug is showing any side effect or it has any other unwanted effect, then it will be taken, the review will be taken, and that review will be noted down and they will work on this. So this is called post-market studies. Post-market studies is done on the maximum patients. Okay, and microdosing studies will be done on the minimum patients. So minimum means how much? First of all, microdosing is non-specific. It can be 1, 2, 3. Next, second phase will be done on 10 to 30. Third phase will be done on 100 to 300. Fourth phase will be done on 1000 to 3000. Again, microdosing will be done on the research center. Then unicentric will be done on the one place only. Multicentric will be done on the one center only. Multicentric will be done on the multiple center, more than one center. Post market studies will be done after the marketing of the drug. Okay. So this is the most important. In this, number of patient is not important. Healthy or unhealthy volunteer is important. So first two is healthy, then unhealthy or patients. Unhealthy or patients. And the name, different name. And you have to understand the notes. So already we have studied about this. So first one is called, it is called microdosing studies, and microdosing studies will give us the data which pharmacokinetic data of the drug. Next, unicentric studies. Unicentric studies will be done on the 100 to 300%, and it will be done on one center or one health center, and it will, this study is called safety and preliminary efficacy. Safety and preliminary efficacy. Okay. Next, multicentric. It will be done on multiple centers, and it will be done on the 1000 to 3000 patient, and this uh, phase is also called safety and confirmatory efficacy. Safety and confirmatory efficacy. Next, fourth phase is called multiple post-market studies, and it is done on more than 20,000 to 30,000 patients, and it is called rare side effects is studies in this. Okay. Next, we are going to learn about different property. Already new molecular entity pre-formulation studies already done. What are pre-formulation studies? The studies which are done on any drug before its preparing or manufacture. These are called pre-formulation, before its formulation. So pre means earlier or before, formulation means compounding or preparation. So pre-formulation means before preparation of the drug, it will be studied, and it is called pre-formulation studies. In this, three things are studies. Physiochemical processes. So three physiochemical processes will be studies. Number one, bulk properties, solubility properties, stability properties. Bulk properties contains crystallinity, polymorphism, hygroscopicity, fine particle characterization, powder flow properties, and bulk density. Solubility properties will be studied, and in this what we will study normally: solubility, partition coefficient, ionization, dissolution constant. Next, stability properties. In stability properties, what we will be studying: hydrolysis, oxidation, photodegradation. Okay. Next thing is that bulk properties. So in these bulk properties, we have already studied polymorphism. Polymorphism means more than one structure. In this polymorphism, external, internal. Internal is called external structure is called habit. So external habit are different types: cuboidal, needle, pencil, plate-like, and star shape. Now, needle or acellular structure is present in nalidixic acid. N needle starts with N, nalidixic acid also start with N. So N needle, N nalidixic acid. Next, tubular structure is found in tolbutamide. So T tubular structure, T tolbutamide. Okay. Next, tolbutamide tubular structure. Next, equivalent is in sodium chloride, NaCl. Another most important point I forgot to tell you is that route of administration and type of dosage form is defined by the physiochemical properties of the drug. Okay. Next, we will understand the very important point. See, very important. What is this? It is polymorphism. In this, we will study the different properties of polymorphism and which one is present and absent. So for example, arrangement of the molecules. If arrangement of the molecule in a crystalline structure will be 3D arrays, regular characteristic geometric shape will be there, and in amorphous 3D, here in crystalline 3D arrangement will be there and regular arrangement will be there, whereas in amorphous there will be no regular or 3D arrangement. It will have random or scattered arrangement. Next, it is regular but it is irregular. Geometric shape will be there, no characteristic shape will be there. Okay. In again, solubility, stability. So crystalline is, since crystalline is more stable, it will have less solubility. But why it is more stable? Because of the regular arrangement or systemic arrangement of the particles. Due to the systemic arrangement of the particles or regular arrangement of the particles, crystalline structures are always more stable, whereas amorphous structure are less stable. Since it is more stable, it will have less solubility, whereas since amorphous structure is less stable, it will have more solubility. Next, differential scanning and calorimetry. So we will find different graph in the scanning and calorimetry. In this, crystalline will show us sharp melting point. Crystalline will give sharp melting point in the calorimetry, whereas amorphous will give a broad melting point. For example, in this, the melting point will be exactly 27.8, but here the melting point will be approximately 25.67, 27, 28, 29, like this, 3 4. Okay, now X-ray diffraction and spectroscopy. So crystalline will give sharp diffraction band. Crystalline structure will give sharp diffraction band, whereas amorphous will give smooth or broad curve. Amorphous structure will give smooth or broad curve. Okay. Next, thermal solid state characterization technique. What are the thermal or solid state characterization techniques? There are three types of characterization techniques. They are called DSC, DTA, and TGA. DSC means differential scanning calorimetry. DTA means differential thermal analysis, and TGA means thermal gravimetric analysis. So what are different types of analysis? They are differential scanning calorimetry, differential thermal analysis, thermal gravimetric analysis. So differential scanning analysis, in this the graph will be between change in entropy and temperature. In differential thermal analysis, the graph will be between change in temperature and temperature. And thermal gravimetric analysis, in thermal gravimetric analysis, the graph will be between change in work done and temperature. Sorry, change in weight and temperature. So here change in heat, here change in temperature, here change in weight. Okay. Next important point, crystalline form converted to amorphous form to increase the solubility. So crystalline form are converted to amorphous form by lyophilization, rapid precipitation, and rapid cooling. Crystalline forms are converted to amorphous forms by lyophilization, rapid precipitation, and rapid cooling. Lyophilization, rapid precipitation, and rapid cooling. Okay. So why crystalline form are converted to amorphous form? To increase the solubility. Now, can you please tell me, if to increase the solubility, crystalline forms are converted to amorphous form, then the drug, which will be any drug substance like any tablet formulation, the substances which are used, it should be crystalline or amorphous. Definitely it should be amorphous. Why it should be amorphous? Because amorphous form has more solubility, and we need more solubility in our stomach. If we are preparing a drug, it should be more soluble in the stomach. That's why crystalline forms are converted to amorphous form to increase their solubility. Already I mentioned earlier that crystalline has high stability and amorphous has low stability. Since crystalline is highly stable, it has low solubility, and since amorphous is low stable, it has high solubility. Okay, the same thing is here also. So crystalline form is converted to amorphous form by three different types of techniques. They are called lyophilization, rapid precipitation, and rapid cooling. Lyophilization, rapid precipitation, and rapid cooling. Lyophilization, rapid precipitation, and rapid cooling. Just remember that. Okay. Next is polymorphism. So what is polymorphism? Polymorphism, single molecule having many morphologies. Example, chloramphenicol. Chloramphenicol is available as palmitate form. See, this is the structure of chloramphenicol. In this, alcohol along with acid is total makes the palmitic acid. Okay, so if after that, if we add this chloramphenicol with palmitic acid, we will get ester. Okay, see this one. I'll show you. Wait a second, please. For example, this is chloramphenicol. What's that? Benzene. So what is that? This is chloramphenicol. When it is added with palmitic acid, palmitic acid means, what is the structure of palmitic acid? Palmitic acid is a type of carboxylic acid, and it has how many carbons? 15 carbon, C CH2 14 CH3 C double bond O single bond OH. So what is that? Palmitic acid. Palmitic acid. Now what will happen? Reaction will takes place. So where this OH, this OH. When the reaction will take place, H2O will remove. If H2O will remove, what we will get as final product? So our final product will be like this. See, one benzene will be there. With NO2, along with that we will get one OH here and one H here. Along with that we will get another carbon here. We will get one C double bond O here and carbon 2 chlorine. Okay. Next, here hydrogen will be there, and this bond will be connected with oxygen. Now I'll show you. Carbon connected, chlorine, chlorine. This will be connected as ester bond, and this ester bond will be connecting the palmitic acid. So C double bond O single bond CH2 14 CH3. So this is our final product. So what's that? That's our final product. And this product is called chloramphenicol palmitate. This product is called chloramphenicol palmitate. Okay. So it is an antibiotic and acts by inhibiting the protein synthesis in the microorganism. Okay. So this part is palmitate part. This part is chloramphenicol part. So it is called chloramphenicol palmitate. Chloramphenicol exists in A, B and C form. Of this, B form is most stable and most preferable form of chloramphenicol. See here, I'll show you. What are the different types of chloramphenicol exist? Chloramphenicol normally exist in 5 different 3 chloramphenicol A, B, C. Out of this, B is most stable form and most preferable form of chloramphenicol. This is most stable or most preferable form of chloramphenicol. So B is most preferable form of chloramphenicol. Okay. Can you please tell me what is the side effect of chloramphenicol? Side effect of chloramphenicol is gray baby syndrome. So gray baby syndrome is the side effect of chloramphenicol. That's most important point. Gray baby syndrome is the side effect of chloramphenicol. Okay, normally side effects are being asked earlier also. So many side effects are came already in the competitive exam. Okay, can you please tell me what are the different parts of chloramphenicol? Wait. C H L O R A M P H E N, again N I chloramphenicol, COL. So CHOL means chlorine. Okay, see, I'll show you the structure here. So here, chlor means chlorine. Then M means amide or nitrogen present in that structure. Again, amide means, what is amide? Amide is NHC double bond O, like this. You will also see. Already I mentioned earlier, na? So this is amide. And presence of nitrogen also mentioned by AM. Okay. So this nitrogen is M. Then PHEN, fan means that phenol ring. Fan. Again, Ni means nitro. Totally NO. NO2 means Ni. Okay. Then one OH will be there, another OH will be there. So what are they? Alcohol group. So alcohol group is denoted by all. What is the suffix for alcohol group? Prefix is hydroxy and suffix is all. This is prefix, this is suffix. Okay. So chlor means chlorine. M means presence of nitrogen. Phen means phenyl. Ni means nitro. Col means all. All is alcohol. So this is the complete structure of chloramphenicol. Okay. Now in this chloramphenicol, three structure will be present, A, B, C. Out of that, B is most stable and is most preferable. Already I have mentioned. Next we will learn the different form, that is what is ABC. See, this chloramphenicol exists in three form. Chloramphenicol palmitate, already I showed you in the board that this chloramphenicol, when it is mixed with palmitic acid, it forms chloramphenicol palmitate, and this chloramphenicol palmitate has three structure, A, B, C. Out of that, B is most soluble, so it is used in dosage form. Okay. Okay, B is more soluble. Next, I will tell you another important note down. It is very very important that palmitic acid has how many carbon, and other acids, see, lauric acid. Number one, lauric acid. Then mystric acid. Then palmitic acid. Then stearic acid. Then arachidonic acid. Okay, so you can be simply remember local made pharmacy student association. Local made pharmacy student association. So in lauric acid you will see 12 carbon. In mystic acid you will see 14 carbon. In palmitic acid you will see 16 carbon. And in stearic acid you will see 18 carbon. And in arachidonic acid you will see 20 carbon. So this is the most important table you can remember for the preparation of GPAT, NIPER or anything. Note it down. Next, polymorphs are of two types. We are studying polymorph, yes or no? So polymorphs are of two types. So what are they? See, reversible polymorphs and irreversible polymorph. Okay. So reversible polymorph is also called enantiotropes, and irreversible polymorph is called monotrope or monotropic. Example is glyceryl stearate. So in the exam, they will ask the question simply like, what is glyceryl stearate is an example of enantiotrope or monotrope. So glyceryl stearate is an example of monotrope. Monotrope means they will not convert from one to another. So if they are converted, they will not come back. Okay. So write there polymorphs. Polymorphs. Two types. What are they? Reversible polymorph and irreversible polymorph. Okay. So reversible, other name of reversible polymorph is also called enantiotrope. Enantiotrope. And it is also called monotrope. And it is also called monotropic. Monotrope or monotropic. Example of monotrope is glycerol stearate. Glyster. You can remember like this, glyster. Glyster means glycerol stearate. Stearate. Glycerol stearate. And what is the example of reversible polymorph or enantiotrope? Example is sulfur. Sulfur is an example of reversible polymorph. So reversible means if a structure was X and it was converted to Y, then this Y will again convert into X. But in irreversible polymorph is if X is converted into Y, then it will convert no, and it will not convert back again into X. So it is one directional and it is multidirectional. Why it is multidirectional? Because it is reversible. Why it is unidirectional? Because it is irreversible. It is also called monotrope, also called monotropic. Example is glycerol stearate. It is also called enantiotrope and example is sulfur. Okay, so that's the important topic also. Next, we are going to understand how to identify polymorph. So how to identify polymorph? It is also important. Okay, so polymorph can be identified by three different types of tests. How to identify polymorphs? Polymorphs can be identified by three tests: DSC, XRD, HSM. So what is DSC? DSC is called differential scanning calorimetry. Differential scanning calorimetry. It is all about temperature. XRD is X-ray diffraction. X-ray diffraction. HSM is host stage microscopy. So host stage microscopy. So DSC, XRD and HSM. So these are the three different types of techniques by which we can identify the polymorphs. So again, you write this: DSC, XRD, HSM, differential scanning calorimetry, XRD, X-ray diffraction, HSM, host stage microscopy. Differential scanning calorimetry, X-ray diffraction, and host stage microscopy. Differential scanning calorimetry, right? Differential scanning calorimetry. Number 2 is X-ray diffraction. And number 3 is hot stage microscopy. Okay. So these are the three important techniques by which we can identify the polymorphs. Next, what is endotherm and what is exotherm? If we study the differential scattering calorimetry, then in this temperature will be there. So it is related to temperature. So to understand the temperature, first of all we have to understand the graphs of the temperature. So for example, so if we put temperature, oh no, not like this. In the detector, if temperature increases, and in the detector, if temperature decreases, there will be two different types of temperature curve. Okay, one is called exothermic, another is called endothermic. So what is exotherm and what is endotherm? See, there is a graph. In this, a substance is there. Okay, you have started putting some temperature from this phase, this area. Okay, A, B, C point. For example, 10, 20, 30. If the graph is like this, then it is normal. If the graph is like this, and if the graph is like this, so three different types of graph will be there. Okay, and out of that, mainly we will study two graphs. What are the two graphs? One graph will be endothermic, and the second graph will be exothermic. Where is the blue pen? Exothermic means like this. So see, this is the initial point. This is the initial point. If the temperature graph completes above, then it is endothermic, and if the temperature graph completes below, then it is endothermic. Why it is exothermic? Exothermic means from the earlier, now temperature is decreased more, and endothermic means from the starting point, now temperature is more of the substance. So that means, see, there are different types of peak you will get. In one peak, what will happen? You will get, okay, if you can take both the peak in same level. So if you take both the peak in same level, still you will see one graph is completed at the top and one graph is completed at the bottom. So what does it mean? In this graph the object is releasing the heat. In this graph the object is absorbing, right, properly, absorbing heat. So when heat is absorbing, it is called endothermic, and when heat is releasing, it is called exothermic. Okay, so exothermic and endothermic graph can be studied in two ways: where it is where it is started and where it is completed. See, I'll tell you again. Started from this point, if it is completed here, it is endothermic. Started from this point, if it is completed here, then it is exothermic. So it is exo, it is endo, and exo is releasing temperature, releasing, and endo is absorbing. Okay, that's most important. Next we are going to study the different types of, so the difference between exothermic and endothermic. Okay, what is exotherm, what is endotherm? Simply endotherm and exotherm. So endotherm will absorb it, already I told you. Endotherm will absorb heat, whereas exotherm will release heat. Okay, next point, endotherm melting point. Number 2, boiling point. Number 3, sublimation point. All these three graphs will be endothermic graph. What are they? Melting point. Melting point means melting of something. For example, one ice cube is there. This ice cube is melting into liquid. So solid to liquid. Remember this point, very important. Solid to liquid. it is melting point. Again, what is boiling point? So right here, solid to liquid. Again, boiling point. What is boiling point? In a container, water was there. You applied some temperature or heat. This water will convert into vapor. The water level will decrease down, and some water will convert into vapor. So liquid to gas. Yes or no? Liquid to gas. So you have to remember that this melting point is from solid to liquid. This boiling point is from liquid to gas. And again, sublimation is from solid to gas. In some cases, the phase change will take directly like this, that the solid will directly convert from the solid will directly convert into gas. Okay, in that case, it is called the energy which is applied or absorbed, or the temperature which is absorbed, is called sublimation energy. Sublimation energy. Okay, so what is sublimation energy? Sublimation energy is the energy which is required to convert a solid directly into gas form. Convert a solid form directly into gas form. Okay, it is called sublimation energy. Next, what is exothermic? In this, transition, temperature, oxidation, crystallization, these all are example of crystallization. TION, crystallization, oxidation, oxidation, and temperature. These are the main major differences between endothermic and exothermic graph. You have to understand it. Wait a second, please. I'm having a call, so excuse me. Hello.
Hello, this is the notification from Telecom Regulatory Authority of India.
So, hello everyone. Can you please tell me what are the different types of analysis are there? or analytical techniques. Thermal gravimetric analysis, gas chromatography, high performance liquid chromatography, NMR. You know all these things. So what are they? They are the example of anyone can tell me please? Okay, one most important part. We are going to learn the different types of hygroscopy. Okay, we are going to learn about the hygroscopicity. What is hygroscopicity? So hygroscopicity is the tendency of a drug to absorb water from the atmosphere. Hygroscopicity is the tendency of a drug to absorb water from atmosphere. Okay, in this what will happen? Hygroscopicity is the tendency of a drug to absorb water from the atmosphere. So need special packaging and storage condition. So to keep what is the degree of in the competitive exam it is asked what is the degree of hygroscopicity. It is most important. Okay, so next, due to the hygroscopicity weight increases. The important point about hygroscopicity is that actually my alignment is not correct na. Wait a second. Due to the hygroscopicity weight will increase. Due to hygroscopicity what will happen? Number one, weight will increase. Weight will increase and physiochemical properties will change, which will lead to the change in pharmacological properties and therapeutic activity. So ultimately hygroscopicity is good or bad? For a drug hygroscopicity is not good. Okay, why? This hygroscopicity will lead to the change in physicochemical properties, which will lead to the change in pharmacological properties and then change in the therapeutic activity of the drug. Okay, next, so to keep the drug safe, what we have to do? To keep the drug safe, we have to do proper packaging. So this is the drug, packaging should be done properly. So need proper packaging. Next, storage condition. Storage condition is also important. Next, there are three different types of hygroscopicity. One is slightly hygroscopic drug, one is normal hygroscopic drug, and one is very hygroscopic drug. So three types. One is slightly hygroscopic, one is hygroscopic, one is very hygroscopic. Okay, so slightly hygroscopic, in this what will happen? Calculation will be done like this. If initial weight was W1, final weight is WF or W2, then change in weight del W equals to W2 minus W1. It is done. And del W, if the del W is in the range of 0.2 to 2%, then it is called slightly hygroscopic. If the del W is equals to 2 to 15%, 2 to 15%, it is called hygroscopic. And if the del W, what is del W? Del W is change in weight. If the del W is more than 15%, then it is very hygroscopic. So these 3 points are most important. You have to remember that. One is del W, either 0 point in between 0.2 to 2%. So how should I write that? The del W is between 0.2 to 2%. Next is more than 0.2 and less than 15%. More than 2 and less than 15%. And third one is more than 15%. So it is called slightly hygroscopic. Slightly hygroscopic. It is called hygroscopic, and it is called very hygroscopic. Slightly hygroscopic, hygroscopic, and very hygroscopic. So you have learned that. Okay. So there are 3 different types of hygroscopicity. One is slightly hygroscopic and very hygroscopic. Slightly hygroscopic. In this, the most important point which is to remember is that one only. In the examination, this information will be asked only. For example, if the change in weight is between 0.2 to 2%, then the hygroscopicity will be which type of hygroscopicity? It is slightly hygroscopic or fully hygroscopic or very hygroscopic. It will be slightly hygroscopic. So the range is only 0.2 to 2 and again 2 to 15 and again more than 15. So 0.2 to 2, 2 to 15 and more than 15. 0.2 to 2, 2 to 15 and more than 15. There are 3 different types of hygroscopicity. 0.2 to 2 and again 2 to 15 and again more than 15. That's it. These are the 3 different types of hygroscopicity, and it is denoted by the change in weight. Why change in weight? Because in hygroscopicity it will absorb water from the environment. Yes or no? It will absorb water from the environment. Due to the absorption of water from the environment, weight will increase, and increase in weight will change the pharmacological properties also, which will lead to the change in physicochemical properties. Physical chemical properties will change in pharmacological properties. Pharmacological properties will change in the therapeutic activity. Therapeutic activity means how the drug will treat the disease or not. That's most important. Next, deliquescent substance. What are the deliquescent substance? The solid substance which absorbs the water and convert into liquid. For example, a substance is there. Take a very highly hygroscopic substance. It was solid earlier. Okay, and it is highly hygroscopic. That means very hygroscopic. Very high hygroscopic. It absorbed more water from environment. Due to that absorption of water, it converted into liquid or gel-like form, mainly mentioned as liquid. So it converted into liquid. So this conversion of solid to liquid due to the hygroscopicity, the conversion of solid to liquid due to the absorption of water, is called deliquescent substance. Absorption of water. Absorption of water is called deliquescent substance. Okay. So according to the European Pharmacopoeia, drug substance is exposed to atmosphere for 24 hours at 80% at 25 degrees Celsius. According to European Pharmacopoeia, drug substances is exposed to atmosphere for 24 hours at 80% RH at 25 degrees Celsius. Okay. So detection of amount of water absorbed will be done in 3 types. In the hygroscopicity, the amount of water will be absorbed. So this amount of water will be absorbed is detected in 3 ways. They are: number 1, Carl Fisher. Not Carl, it's Karl. Carl Fisher technique. Number 2, gas chromatography. Carl Fisher technique, gas chromatography. Number 3 is TGA. What is TGA? Thermal gravimetric analysis. By these three way, thermal gravimetric analysis, gas chromatography, Carl Fisher, and number 4, gravimetry. So by these 4 way, we can identify or we can calculate, detect the amount of water absorbed. So what are the detection process for detection of amount of water which is absorbed due to hygroscopicity? 4 different types of technique. These are Carl Fisher technique, gas chromatography, thermal gravimetric analysis, and gravimetry. Carl Fisher technique, gas chromatography, thermal gravimetric analysis, and gravimetry. You have to remember that gas chromatography, thermal gravimetric analysis, gravimetry, and Carl Fisher technique. Carl Fisher technique, number 1, Carl Fisher technique, number 2, gas chromatography, number 3, thermal gravimetric analysis, and number 4, gravimetry. Okay, now what is Carl Fisher titration? Carl Fisher titration is also called colorimetry. Carl Fisher titration. It is also called colorimetry. So in this, one reagent will be used which is important. Colorimetry. One reagent will be used. This reagent is mainly important only. So what is the reagent? In Carl Fisher titration, the reagent which is used is iodine along with sulfur dioxide along with solvent. Solvent should polar solvent such as methanol. Polar solvent such as methanol and along with that plus base. So what is base? These are electron pair donor. Base are electron pair donors. Base are of two types. These base are of two types. One is pyridine, another one is imidazole. Where did I keep this black marker? It's okay, no problem. So the base are of two types. One is pyridine and next one is imidazole. Pyridine and imidazole. Pyridine is how many membered ring? 6 membered ring containing nitrogen. Yes or no? Whereas imidazole is how many membered ring? Imidazole is 5 membered ring. Imidazole is 5 membered ring. Okay. Now you have to remember one thing, that pyridine is carcinogenic. This pyridine is carcinogenic. And imidazole is non-carcinogenic. So in the question, it may be asked like this. In the Carl Fisher titration, so the base which are used are of two types. One is carcinogenic, another one is non-carcinogenic. So there can we ask the question like this: pyridine is a carcinogenic base used in the Carl Fisher titration. Or imidazole is a which of the following statement is correct or wrong? In this statement they can ask imidazole is a carcinogenic base which is used as a reagent in Carl Fisher titration. It is true or false? So it is false. The true is imidazole is a non-carcinogenic substance, non-carcinogenic base which is used as a reagent in the Carl Fisher titration. One question. Next question, what are the reagent used? So iodine, sulfur dioxide, solvent and base. iodine, sulfur dioxide, solvent and base. Okay, so in Karl-Fischer titration the main important points are 2 points. Number 1 point is reagent. Which reagent? Karl Fischer reagent. What are Karl Fischer reagent? It's iodine plus sulfur dioxide plus solvent plus base. So solvent is polar such as methanol or ethanol, and base are two types. What are they? One is carcinogenic, that is pyridine, and other is non-carcinogenic, that is imidazole. That's most important. Okay, C and C. NC means non-carcinogenic, C means carcinogenic. Okay. Okay. Next point, that in the Karl Fischer titration or colorimetry, what will happen and how will be the graph, and what are the main important points related to the graph that is asked in the competitive exam. So the graph will be like this. Okay, in this colorimeter, and the graph is like this. So in this, number of water and drug completed molecule. This point defines the number of water which in drug completed molecule. Okay, so in this the reagent will be added with osmium water, then intermediate will form, and after that end product will form. Okay, this intermediate such as alkyl sulfate interacts with the water and produce current. This current is measured by calorimetry. Okay, that's why Karl Fischer is also called calorimetry. You understand or not? Next, see Karl Fischer titration. In this what will happen? The reagent will be reacted with osmium and water, and it will form an intermediate. Yes or no? Then this intermediate will form the final product. Then that intermediate will form the final product. This final product will be alkyl sulfate. So what is the final product that's formed in the Karl Fischer titration? It is alkyl sulfate. That is more important one. So alkyl sulfate is the final product. Okay, alkyl sulfate is the final product which is found in Karl Fischer titration. How this is treated? So in this what will happen? The alkyl sulfate will interact with the water and produce water current. The alkyl sulfate which is produced is the final product. The alkyl sulfate will interact with water. Interact with water. So interaction with water will produce current. It will produce current. Yes or no? And this current is measured. This current is measured, and by this way we can understand the presence of water inside the drug substance. Next, gas chromatography. We will learn that in next live session. Okay, thank you so much.